Okay, so we can get started. So quick poll. Who's all set with programming assignment 0? Show of hands, all done with programming assignment 0? Half? How many of you have gotten started on programming assignment 0? A good number. Who is making solid progress but just started? Some. Who hasn't started programming assignment 0 at all? Okay, good thing. None of you raise your hand, right? So that is on track to be due tomorrow evening. The due dates are always set to be 10 p.m. I don't set midnight due dates, just so that everybody keeps a sane daily schedule. Also due tomorrow, the quiz. So if you haven't at least started to make some attempts at the quiz too, definitely get started on that, right? The quiz is basically just reviewing things that's been covered last week and this week, and really only up to Monday's class, right, or Tuesday's class. So it's topical, it's a good preview of what types of questions to expect on the exams. We're launching now into the key things that we have to learn really that are different about C. Overall, C has a lot of things that are quite in common with Java. And the main thing that we have to get used to is C now allows us to use this programming feature called pointers. And maybe we'll talk about this from this perspective, right? Have we encountered something in Java that's kind of like pointers before? Yeah.
Like the variable in a for loop, I know like
Okay.
used arrays, I've used a for
So the iterator, right, the indexing variable in a for loop is kind of like, has some things that may be similar to array access, sure, so that's a little bit related to pointers. Anything else that might be similar in Java that we've encountered before? Yeah. Good. Good, right? So when you're building a linked list in Java, there has to be this notion of a reference to the next item in the linked list, right? That reference, the concept of references in Java, really is just exactly the same thing as pointers here in C. Any other potential places we've seen something like it before? I think those are the main ones. There could be other good examples, but a key point here is pointers as a language feature are really important. Almost every language feature you can think of in Java, in some way or another, are enabled by pointers. And what are pointers? Pointers are really just addresses. They are a number that represents where the data is stored in the computer's memory. So we've been working on a lab code, which is available in the repository. And on Tuesday's class, we worked through the first few pieces of it. Lessons 1, 2, and 3, I think. Lessons 1 and 2. So we have our pointers lab, and we can run the pointers lab. And we went through lesson 1, where we just showed that, OK, we instantiate some number. We declare and define a number of unsigned int type. We grabbed a pointer to that number using these two operators, the star operator and the ampersand operator. We inquired and talked about how pointers are themselves 8 bytes long, so 64 bits. So we use 64 bits in total. to enumerate the places that data can be stored in memory. And this number, you can either print it out as hexadecimal format, right? Hexadecimal is just base 16. Base 16 is bigger than the decimal format that we're used to. So in decimal, we have number digits representing all the way 0 to 9. And in base 16, you need 6 more, right? So you have to have a character that represents 10, 11, 12, 13, 14, 15. And to do that, we're used to using A, B, C, D, E, and F to represent that. And so we write down the hexadecimal. The 0x emphasizes that what's being printed out here is a hexadecimal number. And you can also print that out as a decimal number like this. We're going to work through a kind of spreadsheet, which is also posted on Canvas, to illustrate this idea, right? And I'm going to create a couple extra columns to the left here. So I'll have several columns here. One is going to be called the data type. Another is going to be called the, what should we call this? The variable name. And I'm going to illustrate what's happening in the code using this picture here, right? So this picture here, everything in this thick black box here, this is what's going on in the memory. And in fact, instead of drawing the black boxes where they are now, what I'm going to do is I'm going to only draw the black box just only where contents of memory are, right? So I'm going to draw a thick border indicating everything in this box here is what's being stored in memory, right? And memory is just this long sequence of cells in the computer, and they have addresses. So the addresses, we would start from low addresses, say 0x0, right? So just the 0 address, all the way up to a very large address, 0xf, f, dot, 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 f, f, right? Does it make sense that here I'm writing that down to indicate just some really big number? Makes sense, right? And we can basically run a little simulation, right? We'll start slow in the code, and then we'll speed up a little bit. But basically, line by line, you can draw what's happening in the computer as you run this code, right? So who wants to take a guess what we should do, just to indicate what we're doing is to declare and define a variable number equals 500. Where should everything plug? So what's the data type? Yeah, just shout it out. OK, good. And then the variable name? Number. Do we know what the address is? OK, we'll skip that, right? So that's the tricky thing. And the number is 500. Now, I'm going to draw some more pictures here. So who wants to take a guess at how many cells I should really occupy to store 500? Right? If each cell is 1 byte, how many cells should I use to allocate to store 500? Yeah. Shout it out. 8? Not quite. So typically in the C language, what we're used to, just a plain unsigned int, is going to be 4 bytes. Right? 4 bytes, 32 bits. And we'll study kind of this in more detail kind of in the next chapter on data representations. But this is a preview. So we'll say I'm going to draw a thinner box border here, just to indicate that this 500 is being stored in these 4 bytes. And I'm going to merge the cell just to emphasize that too, right? This number 500 as a decimal number is stored in these 4 cells. Good. So far, so good. Can I fit this kind of in a more compact way? Yeah, that's a clearer view. Okay, next thing, next line of code, line 15. What should I do to indicate what's happening on this line of code? Yeah, what's the data type? Good, right? So this is a new type of data type now, right? The pointer itself is a data type. Just as we're used to, there's being ints and bytes and, I don't know, characters and object data types. A pointer itself is really just a data type. Its data type is unsigned int star. That's the data type name. What's the name of the variable? Yeah, pointer. And what's its address? Kind of a trick question. Hmm? No, not quite. We actually don't know this address, right? We haven't figured it out yet, right? So both of these things have been question marks, right? But now what's going to happen is we're going to read this little piece of code I've highlighted here. Right? How do we understand what this ampersand means of? Well, ampersand in C, it is called the address of operator. Right? We can call it address of. Another name we sometimes might give it is called referencing operator. But kind of just to emphasize that these things are very different, right? Just to kind of like disambiguate them, I'm going to try to go by the convention of this ampersand is called the address of operator. What does it mean to take the address of? So address of number. All right, so address of number. So this address of number, this is the address of number. And we're going to grab the address of number and we're going to store it as pointer, just like so. And just like before, every number that we're going to write down is going to take up a certain number of cells. So who wants to take a guess at how many cells I should allocate for this? Yeah, just shout it out. 4? 8? The answer is 8, right? We actually saw this in the program already. The size of a pointer, the pointer data type, which is size, the type unsigned int, its size of, the program tells us it's 8 bytes. Right? So I'm going to allocate 8 bytes to store this number. So by allocating, I mean I will draw 8 cells, 4, 5, 6, 7, 8. I'll merge the cells, and I'll center the cell, and I'll draw a light border indicating that all of this is really now storing this one number. And we can take a look at the code, right? So the code keeps executing. What happens next is it's just going to print out various things. So none of these operations actually write any new numbers into memory, around in memory, but rather we're just now inquiring what these various values are. So first we print out number, right? So number is 500. Then here in this printout, it's telling us more, right? So I've now got this pointer equals 0xFFF, so forth. Where can we write down this new piece of information we've discovered? Right, what is this number? Where is it in our picture here? Yeah?
Is that
The pointer address?
Address of the number.
Address of the number, right? What was pointer? Pointer was address of, ampersand means address of number, right? So this value here, this is just simply the address of the number. And what was the address of number? Here, right? This is where number lives. So originally I had jotted this down as just as a placeholder. Now we know its concrete value. This location, this address, is this number here. And where else does it show up? Yep, in the contents of pointer. So this number, again, it was a placeholder. This number is being stored as these 8 bytes here. Right, and I'm gonna emphasize what's going on here. What's the actual stuff in memory? Like what's real and what's just kind of a cartoon representation here. What is concretely something that you can go into the computer and see, aha, this actually exists in the computer, in your memory. Yeah.
It's just numbers.
Well, so what I was getting at is I drew this thick box, right? This column here, only this column is what's actually the memory. Everything else to the left of these, all these columns to the left, these are just kind of our notes to understand and kind of annotate the contents of the memory. This is what's in memory here. And what we've done here is this address of the memory, well, we've written it down. We've like grabbed the address of and put it as a number that we're storing. Right? This is kind of an important point where we're going to eventually somebody's going to ask some questions about, so where is this stored? Just remember, the only thing that is real here is this column here, boxed in by the heavy border. Marching through the program, so this part of the program just emphasizes telling us that the way pointers are stored are 8 bytes, so it takes up a bigger box, 8 cells there. And what do we make of this information? If we wanted to somehow put this somewhere, yeah.
It's like the address, but in number form.
Yeah, so it's the same thing. It's this number here. It's this 0xFFF hexadecimal number. But now we're just going to put it in a more human-readable decimal format. And to emphasize that, maybe I'll just say, by the way, how do I do a line break? There. By the way, this is just that number there. Parentheses, by the way, 0xFFF, that is just this huge number in decimal. Any questions before we go to the next little lesson? Yeah. Yeah, the contents is just an array. It's a giant array of bytes. What's memory? Memory is just a giant array of bytes. What are the indices of the array? Right? Array index I. Where's I here? Yeah. Yeah, it's just the address. The address is indexing into this array of bytes that is the memory. Yeah.
So like in this case, like would this be like a bad use of a pointer since the pointer takes up more bytes than the actual number?
So question is this somehow bad use of a pointer? Is it somehow wasteful that we're using 8 bytes to represent data that itself only occupies 4 bytes? I would say don't worry about that. The memory is very, very tall. There's a lot of space. So pointers being 8 bytes is perfectly reasonable and plentiful, or is a perfectly good design choice. And we talked about this a little bit, right? Why are pointers 8 bytes, right? You know, we're used to integers just being stored neatly in these 4-byte integers. Seems like overkill, right? Seems wasteful that pointers are always 8 bytes. And, you know, there may have been a time where, sure, we want pointers just to be 4 bytes. But then what happened is if your pointer is only 4 bytes, your contents can only be so tall. Right? So as the contents grew taller and taller, your addresses go beyond the range of 4 bytes. And that's why they moved in 2004 or 2005, the mid-2000s, so that pointer sizes are always 8 bytes. Right? Most modern computers are 64. OK, let's check on the slides. Yeah, so we basically talked about all these objects, all these topics. Next, lesson 2, dereferencing pointers. So we'll keep going. We'll allow the code to run. So I moved return 1 down a notch. So now the program runs through lesson 2. And we can keep doing the same thing, right? Line by line, just to be very pedantic. Line by line, we can take the code and we'll draw a picture of what that corresponds to in our cartoon on the Excel sheet here. So who wants to say what we should do with line 23? How do we illustrate what's going on in line 23? What's the data type? Is it unsigned integer? Is that the data type? Yeah, we've got a data type called unsigned integer star is the data type. What's its variable name? Second pointer. What's its address? Don't know. Just question mark, actually, right? And just to kind of emphasize that this might not be contiguous, I'm going to pad it by some cells, right? There's no claim here that all of this belongs in the same continuous stretch, right? So some distance later, maybe we now have our second pointer. And what's being stored? What is the content that's being stored here? What's on the right side of the assignment operator of the equal sign? Yeah. The number 1,000? No, not quite. What I'm staring at right now is really just this highlighted piece here. Yeah. Yeah, just read it off, right? What is ampersand? Ampersand is address of number. What's address of number? Yeah, where's number? Number's here. What's its address? This. All right, so same thing. Second pointer is really just the same thing. How many cells does it occupy? 8. 1, 2, 3, 4, 5, 6, 7, 8. So I'll merge the cells, and I will center the cell, merge and center cell, and then I gotta draw a box. Outside border. How do I blind break here? There. Okay, so same, right? That's the cartoon we keep drawing. Line 24. So line 24 is now something new. So line 24, I've got now this star, right? So just as same as before, when we see star, I'm going to ask you to think star just means dereference. So what does it mean to dereference second pointer? Yeah. Go to the contents of the address, right? Yeah, maybe we'll just say that's that, right? Dereference just means go to the contents of the address. So second pointer, what's the value of second pointer? It's this number. And dereference just goes from address to contents. So let's go to that location, 0xFFF. Where is that in the memory?
So I believe that accesses number.
Yeah, so okay, so it accesses number. So here's our address, and dereference that location. We go from this cell to here. So now we are at this location. We're looking at this location in the memory. And what is the task that's being done on line 24 do? Yeah. It puts a 1,000 there. So it goes to this location and says, now this number, this location, this value is 1,000. So it plops 1,000 there. Right? So from there, all of the rest of the printouts make sense. Print out the value of second pointer. What should this print out? 1,000. 1,000, there. I'm going to delete this line 27 for now because it misses the point. Rather, what I will do is star pointer equals, now this line of code, line 27. What will this print out? Prints out 1,000. Now, how did that make sense? I thought pointer was 500 before. Why is pointer now, dereferencing the pointer, now say 1,000? Yeah. Because I changed the value, right? I already changed the value, right? This is called pointer aliasing. Pointer aliasing just means that what you could do is you can grab multiple pointers to the same location, right? Here I have pointer and I have second pointer. Their values are really the same, so they really all point to the same location in memory. And so if I change them from 1, I go from here to here and change the value here, well, the other alias pointer, the other pointer pointing at the same location, if you dereference that value, it sees the latest change, right? So it makes sense that this is 1,000. Anything I can clarify here? Does this make sense, or this is obvious, or this is interesting? Questions, comments? Yeah.
So if you print out number, does it print out 1,000?
So let's just print out a number. Good question. Who wants to take a guess? What happens? Who thinks it should print out 500? Anybody in the 500 camp? It's okay. We got some hands for 500. So let's think about it though, right? So is there anywhere in the computer now that still has 500, right? 500 has completely disappeared, right? Remember, this is what's real. This is the state of the computer. There's nothing in the computer anymore that has 500. Wherever that was 500 before is now 1,000, right? So number, we're asking to print the variable number. Well, number is stored at this location. We're asking it to print this location. It's going to print 1,000. We can confirm that. Make, run the program, 1,000. Sounds good? That was a good question. Anything else? Yeah.
So because it's changed to 1,000 after the time of pointer, if you did it before that, it would still print out 500.
So where are you suggesting we take a look?
Like right under unsigned.
Give me a line number.
Let's say 23.
After line 23, right? So let's print question, right? New query. Let's inquire the pointer after line 26. At line 26. Question here, 500. So as you say, right, the program has a state. So here, if you're printing it at this line takes place before you've overwritten 500. So anything you print here, it can't predict what's going to happen next. So here, it still prints 500. Yeah?
So when the star symbol is next to a data type, that means the pointer. When it's not, that means getting what's at the pointer, or what's after the address that it's storing.
So just to kind of summarize, right? Just to demystify what the star and the ampersand are, just think star means dereference. It goes from address to content. Address of the ampersand means address of. It goes from contents to grab the address. Right? So this is kind of a helpful little notation there. No? Good. Sounds good? Let's move on to lesson 3. So we're in lesson 3 now. So let's, lesson 3, right? So lesson 3, the code here is just a bunch of printfs. And so we're not actually going to make any new cells here because we're not declaring and we're not defining any variables. But still, we're going to see something interesting. All right, so lesson 3, first task is we are going to inquire what's the size of the int type. What's the prediction on what this should print? 4, right? We already illustrated the size of an integer is 4 bytes, indicated by here I have 4 cells to store an integer, for example, an unsigned integer. Line 41, this printout, trivial. We've already kind of emphasized this plenty enough. The size of pointers is 8 bytes. And then line 42, this is just going to print out the decimal, right? It will print out this 14 whatever billion trillion number, like so. And then what we're going to do is we're going to inquire on printing the value of pointer plus 1. Right? What does it mean to do pointer plus 1? What does plus 1 mean, just in general? Add 1. Right? Does it always add 1? Right, so what I'm emphasizing here is adding 1 means, in C and in a lot of other languages, right, operators such as add, subtract, multiply, all of these operators can be overloaded. Right? What does overload mean? Have we heard of the term overload before in Java? Yeah, overloading in Java.
Redefine from the base meaning?
Yeah, redefine from the base meaning. Can somebody think of like an example of overloading in like natural language, in the English language? I'd be kind of creative here. Overload. Yeah. Cap?
Yeah.
What does cap mean? What does cap mean in the base meaning?
Caps is like a hat, but then caps is overloaded. New slang meaning is like calling something fake. Or,
Okay. So I've never heard of that term before. So cap as in calling somebody fake. Sure, right? So cap, this word, cap, it's got a lot of meanings, right? Cap as in a hat is one meaning. To cap as in I'm going to put a lid on something, that's also a cap. Cap as in like some short form for capitalist. I don't know where the term is. Or cap as in meaning that somebody's a fake. Right? So this word, CAP, has a bunch of different meanings. Here, this symbol, plus, means a lot of different things. Right? If the data types involved are integers, it behaves as we expect, right? 4 plus 1 is 5. But if the data type here involved is something else, right? What's the data type of pointer? Long int. What's the data type of pointer?
unsigned int star.
Yeah, up here, right? Pointer data type is unsigned int star. It's an unsigned int star data type. So when you do plus 1 on an unsigned int star, its meaning is no longer just plus 1. It means something else, right? Notice here, pointer plus 1 is not 1 more than the last value, it's 4 more. Why 4 more? Yeah.
4 bytes.
What's 4 bytes?
The unsigned int, so if you add 1 to it, it's just going to add another byte to it.
Good, right? So let's look at our cartoon here. What is it trying to illustrate? Unsigned int star, what's the unsigned int star here? It's this address value, right? It's this number. And plus 1, well, what plus 1 is trying to do is to get at the next location, which would be the next unsigned int, right? So it would be this address here. And just to kind of make this less confusing, I'm going to make this not contiguous, because it doesn't have to be, right? Plus 1 would be whatever this address is. Numbers address, the next address that could be the next unsigned int. Does that make sense? Yeah. What if the pointer is not int? So let's exercise that, right? So I'm going to go through all of these places. And hopefully this is not too much work to modify. Okay. And I'll comment out the rest of the code. So what I've just done now is I'm changing the data type of number to unsigned short int. Any guesses on how big an unsigned short int is? 2 bytes. Right? And how will we modify our picture here to illustrate that idea? So what's the data type change? All these places are now shorts. Right? All these become shorts. And what's the other change to our picture that has to change? Short is 2 bytes, right? So 1,000, we would be storing it in just 2 cells. So I'll delete, if it allows me to, delete a cell. Delete, delete. Nope. Delete the middle one. That just modifies our picture a little bit, right? And let's run the program, right? So I think this should compile. And what's changed? So what's the data type of pointer now? Yeah. Good. So pointer is now an unsigned short int. And what does the meaning of +1 mean if pointer is unsigned short int type? It now becomes add 2. So see that? Here, it's pretty smart. It knows that pointer is unsigned short int type. So the meaning of +1 makes sense. It is the next address location after you're done storing that unsigned short int, right? So it's no longer +4, now it's +2. That makes sense. All of this is very good. Any kind of questions to clarify what's going on here? Ready for lesson 4? All right, let's do lesson 4. So I'll increment my code to allow me to get to lesson 4. Lesson 4 is a big one. So let's run it. So lesson 4, printing each byte of an integer. OK. So who wants to, so we've got some pictures that we should draw now. Who wants to walk us through drawing line 51 in our cartoon? OK, so we got a data type. Data type is unsigned car star. Variable name? Car pointer. What's its address? We don't know. Could be anything. Right? And what value is it grabbing? How do we understand what it's grabbing here? Yeah, it's casting it, right? So it's going to grab the value of pointer, and the value of pointer is just this number again. And so we'll store that in memory. How tall should it be? Yeah, so all pointers, right? Even though this is now a unsigned car star pointer, it also is stored in 8 bytes. So 1, 2, 3, 4, 5, 6, 7, 8. We're going to merge and center it, draw a border. Right? So it just copies down that number again, but emphasizing that it's now casted as a unsigned character star type. Good. So we've drawn a picture for this line of code here. And now I think we have the interesting thing, right? The next thing we'll do is line 52, 53, 54, 55. We're going to print out some numbers. Okay, so what happens first? So first we'll print out a address. And here in this plus statement here, what's going to happen? Right? Again, we recall like plus is like the word cap. It's overloaded. It has different meanings depending on the context. So what does plus do here? What's plus working on? Yeah. Okay, so the plus operator here is working on character pointer, which is of unsigned character pointer type, of unsigned char star type. So what does plus 1 mean then? What should plus 1 mean? Should add 8 bytes? How many bytes is a character? A character is just 1 byte. Right? So here, in this context, the plus just means plus 1 size of character pointer, so it's plus 1. So plus 1 actually means plus 1 here. Right? So we'll see that in the code running. We said byte at, well, there's the address. Here's plus 1. Plus 1 is indeed plus 1 of the previous value. Right? Plus 1, plus 1, plus 2, plus 3. There. What's the second element we're printing out? So %d, we're going to print out a second field. How do we read what's highlighted there? Yeah.
It's the contents and the address of the car pointer.
Yeah, right. So star means dereference. It means the contents of character pointer plus 0. Contents of character pointer plus 0. Right? Contents of character pointer is this number plus 0. Right? So it's going to go to this location. Where's this location? It's up here. It's this location here, and we'll print the contents here. Right, so you can kind of see what's happening now. I'm printing through each subpart of the number. Right? This number was originally stored as 4 bytes, and now I'm printing out each byte that constitutes the int. Does that make sense? So with that, how do we interpret what's happening here? Why does it say 232, 3, 0, 0? Who thinks that this is just some random situation, just some random output? Who thinks that we could decipher what's going on here? Okay, good show of hands. Right? We could try illustrating what this code is telling us, right? It tells us that the byte at where number is stored there is 232. Right? So again, like we're emphasizing that all this is doing is it's getting at each individual byte of the integer, right? So it says that this value here is 232. The next one is 3. The next one is 0. Next one is 0. And somehow all of this combined was encoding the number being 1,000. So I'll write 1,000 there. Merge, center, right? So we have to figure out what does this make sense? How does this make sense? That somehow the byte values being 232, 3, and 00, that encodes 1,000. Yeah.
So all the address together and the bytes together gives shows the content of 1,000. Is that what you're trying to say?
Good, right? So taken together, these 4 bytes represent 1,000, right? And the way that this is taking place is these values, right, each of these cells is representing different pieces of 1,000, right? You'll notice that if you take 3 times 256 plus 232, what's 3 times 256? 768, 232. The sum of these two numbers, why is it not evaluating, equals this plus this. It adds up to 1,000, right? Somehow Excel is not evaluating formulas right now. I know there's a hotkey somewhere that I must have hit. But 232 plus 768 is 1,000, right? So this is saying that essentially the way it's storing 1,000 is there's a 3 in the 256th place, right? Just like in decimal numbers, you have the tens place, the hundreds place, the thousands place. Here, this is saying that there's a 3 in the 256th place. 3 times 256 plus 232 is 1,000, right? And the way we've gotten at that is we've gone through this number and printed out each byte one by one. Yeah?
So that box would add p times 232. Really, it could be 232 times 16, or not 16. Not 16, it would be 232 times
1.
16, yeah, 16 is 0.
Right? This, just to kind of make this emphasize that this makes sense, it's 232 times 1. Right? And what does this 0 encode? Right? If we want to make this note very clear, what does this 0 mean? Yeah. So this 0, really what this means is it's 0 in the 65,536th place, right? This is 0 times this number, right? What is this number? 65,536. This is 2 to the power 16. Right? And then finally 0 in the place of 2 to the 24. Yeah. So this is kind of previewing kind of what our second chapter of this class is about, but here this is a nice opportunity to see this in action in the memory. Yeah.
I just want to know, where's 256 coming from again?
So where does 256 come from? Yeah, just shout it out.
16 squared.
Yep, 256 is 16 squared. That's true. But more fundamentally, what is it then? It's 2 to the 16. 256?
Yeah, 256.
No, 256 is 2 to the 8. Yeah, 2 to the 8. Right? And why 2 to the 8? Where did this 8 come from? 8 bits in a byte, right? Yeah. Okay, so that's lesson 4. Let's look at lesson 4 code. I think this is junk. This is just a leftover stuff. I was illustrating some concept from before. Just ignore this. Anything that we can do here to kind of play around with this? Like, let's just pause on lesson 4 for a little bit, right? Any questions that can help clarify the concept? Or would it be helpful if we like run through another example? We got some hands raised, yeah.
What happens if you try to add 4? Would there be like a memory overload?
Add 4 where?
In like char pointer plus 4 or
So you want to keep going, right? So I've been printing this character pointer +1, +2, +3. What if we do +4? What's going to happen? Where does that look like on our picture here? Yeah, so it's going to say, well, please go to this location here. Right? This is the address of number +4. It's here. Is this anywhere in the memory? It could be anything, right? Undefined. It might be something, but we could just run it, right? Let's see what happens. Yeah, so it didn't like that, right? The address sanitizer, right? We compiled using GCC with the address sanitizer. This address sanitizer is going to make sure that the things that you do in the memory don't do something undefined, such as trying to get at this location that's not involved in this program, right? This is the address sanitizer saying, stop right there, we're doing something strange. Yeah. Anything else we can illustrate as a hand raise or no?
For the Linux part, I tried to run the gcc-g-vault and it gave me like
Hmm?
do I have to like do like the make sentence and then do the GCC?
Yeah, so let's review what's going on here, right? What happens when I type make? So I typed make here, yeah.
It runs the new file, which has the finished compiled file.
Yeah, so what happens when I say make is it goes to the make file defined in the folder here. Right? It sees that, aha, you have a make file, capital M make file. And it runs the recipe defined in the make file, right? So it says the recipe for compiling the program called pointers is to follow this set of recipes here. And by following that recipe, it will include the address sanitizer in the compilation process. And so when we run the program, it gives us this error message. We could elaborate on this. Well, what happens if we compile without it? Right, so I'll just manually compile. Instead of using the make file now, I'm going to compile again without invoking the address sanitizer. So now we've made a version of the program without the address sanitizer. We can run it. And remember, right, this program right now is doing something weird. Right? We're saying, get at this memory location, which is not involved in this program. Right? It's saying, like, what's the contents of this cell? Well, we don't know. What does the program do? It keeps running. So it didn't stop this time. And it says, oh, yeah, that byte value, that's 172. Where did this 172 come from? It's not from anywhere, right? It's just some, who knows? I have no idea where this 172 comes from. It says that that's 172, but that could be anything, right? It could be maybe some part of this. It could be somebody else's program. This truly is undefined. It could just be residual data in the memory, undefined. Anything else we can play with here? Yeah. 1,000 here. What about it? The 1,000 is the number, right? How about we try something else? You know, let's, who wants to give me just some other number? Just to emphasize that this is how it works. 300. Bigger, give me a bigger number. 7,000. Okay, 7,000. We can try with 7,000. So let's change the value to 7,000. And we'll just run the program again, right? So now I'm going to delete this, delete this, delete this, delete this. We're going to get to 7,000 somehow. And we'll run the program. We'll see what it prints out. /pointer. It tells us this, right? So what does this 88 mean?
88 times 2 is 0.
88 times 2 to the 0. Very good, right? So it just means 88 times 2 to the power 0, which is just 1, right? So 88 times 1 is just 88. What does this 27 mean? 27 times 2 to the power 8, which is equal to 27 times 256. Right? And what is that equal to? 6912. Right? 88 is 88. So these two numbers added together, indeed, 7,000. Right? So this is just getting at like the way we've stored 7,000 is broken down into these individual bytes in the memory. And by playing with pointer arithmetic, we can access those individual bytes. And just kind of rounding out the concept here, right? How come we were able to do that? Like, what did we change about, what was like the kind of key trick we did here? Yeah.
Change the pointer to a character pointer instead of a int pointer.
Yeah, this whole time we've been playing with this character pointer, which has been recast, right? It's been casted from originally this was a whole integer pointer. Now we recast it as a character pointer so that every time we get +1, we get at the individual bytes instead of just skipping the whole number altogether. Very good. Let's keep going. Lesson 5. Lesson 5 is fun too. I guess, okay, this is why I have slides, right? So just final point to make about lesson 4, which is there's this terminology called big endian, little endian. So who wants, based on what we've seen so far, right? Based on what we've seen in lesson 4's lab, what type of machine are we running on? Yeah, so maybe to clarify, right? What is the most significant byte here? What does most significant mean?
I had to guess that not like the most important.
Yeah, so out of these, what is most important? Like, which number would you care most about? Yeah. It's this byte, right? This byte is in the 2 to the 24 place. It counts a lot, right? Here, this byte, you're just adding ones. This guy here is adding 2 to the 24, right? So this is significant. It's the most significant byte. This is the most significant byte, right? So most significant byte, less significant, least significant byte. Which came first? Good, right? So what do we mean by coming first, right? So if we look through the look through the memory, just starting from address 0 all the way through, what came first? The least significant byte came first. So this byte is least significant. It's LSB first. This is a little endian computer. Yeah.
Why is that one the most significant? I know that it's like it has the most like information, but like in this example, right, it's not actually equal to anything, right?
Yeah, so let's, so why is this most significant, right? So right now this number is 7,000. If I just casually, I don't know, I fat-fingered this and thought this is 1, what does this number turn into? It's 7,000. What's being represented now is 1 times 2 to the 24, whatever that is, plus 7,000, right? So just by casually changing what this byte value is, it significantly changes your number, right? So that's why we say it's significant.
So it's the one that has the most impact.
Yeah, that's a good way to put it. It's the one that has the most impact. Yeah.
So we describe it as the most significant, least significant in a general sense. Like, because in this example, it's 0, but like, it's still the most significant in the general like memory.
Yeah, 0, is information. 0 means the absence of, right? Don't knock on 0. 0 means 0. Right? Or just because it's 0 doesn't mean it's not useful information. Yeah.
So it being 0 there, like that's just a representation of the number at that particular byte. But even then, big endian holds the most storage there in comparison to the other three.
That's right, right? This byte here is the MSB, is the most significant byte of integer number, of this integer number. Yeah, so this is a little endian machine. And most computers that you encounter nowadays are all little endian. Why? It's just kind of historical quirk. There was once a time there were big endian machines and little endian machines. And it just so happened that little endian machines became dominant. Okay, lesson 5. All right, so let's increment our program counter. Now we can run through to program lesson 5. And let's, again, right, we can draw pictures here. So line 59 declares and defines a variable. So that tells us we can draw a picture, right? So who wants to just shout out to me what to do on our picture here? Just make, I don't want that either. Let me make more space in our cartoon. Okay, line 59 of the source code. What should we draw? What's the data type?
Unsigned integer with 2 stars.
Yeah, the data type is unsigned int star star. That seems weird. It's fine, right? It's a valid data type. What's the variable name? And what should we assign to it? Again, right? Just to make this not scary, when we see this, how do we interpret it? What's the ampersand mean? You can scroll to the top. Ampersand means address of pointer. So how do we do that? What is address of pointer? Yeah. Yeah, so it's currently a question mark, right? We didn't know yet. But pointer is here. Pointer lives in memory. And it's got an address too. But up to this point, I haven't asked, right? I haven't printed it out yet. So just as a placeholder, we'll call it, it's the address of pointer. And what we're doing is pointer to pointer as a placeholder is going to be ampersand pointer. How tall should this be? 8 bytes. Yeah, it's a pointer, so it's 8 bytes. So I will merge the cells, center it, and draw a box around it. And where does this live? Do we have enough information to plug this in? We don't know, right? We haven't asked. All these are all question marks. They're somewhere in memory, but we haven't asked. Right, so now we can run the program. Right, so the next 3 lines, the program will print all this out. Make, run. So the program runs, it tells us more information. And where should I copy and paste all this new info? What is this now?
So that's the address of pointer.
Yeah, the address of pointer. So first of all, where is this being stored, right? So this can show up in several different places here. This new information that we've gathered, it's the number that was stored here. So we can write that down. And what else does this represent? Yeah.
It represents the address of a pointer.
Yeah, so this is the first time we've inquired, right? This pointer lived somewhere, and it has an address, and now we have information enough to say, oh, well, it was this address. So keep going, right? The next two lines are interesting too. The next two lines, you can take a look at the source code, is going to print out star pointer to pointer, and then star star pointer to pointer. What should we do when we see a star? Yeah. We should grab the contents of that pointer. We should grab the contents of that address, right? So I've got this number here. We grab the contents of that, so we go to here, right? So we go from here. Sorry, I'm confusing you all. We go from here. The star just means go from the address to the contents. So this location in memory is up here, and grab its contents, right? So it will print this out. So kind of tricky thing here is, how come this number here doesn't match what I've highlighted here, right? So these two things I've highlighted in the terminal and in Excel, how come they're different? Yeah.
Is it because you casted it to something else?
Is it because I casted it? No, not quite. Yeah.
Did you compile it again between runs?
Because I compiled it against in different runs? Yeah, certainly. So all kinds of factors, right? I've run this program several times now, right? When I first jotted down this cell, that was like many, many runs of the program ago. Now, like 40 hours later, things have been jostled around a little bit. I've changed what the program structure is. I've run this program many times. Somebody might have logged onto iLab and hogged a bunch of memory space. So it's fine, right? This number is now slightly different. Still illustrates the same idea. It's just saying that go to this location, pointer to pointer, this location, and print out this address here. All right, third line of code. What does this do? And how come now we have a suddenly very sensible number, 7,000? That side of the room is really quiet. Yeah.
It grabs the data that is inside inside the original number.
It grabs the number again, right? Okay, so maybe what I'm getting at is now I've encountered 2 stars. Who wants to guess what does 2 stars mean? Yeah.
It's pretty much a double, just doing it twice.
Doing it twice, right? Yeah.
So it's taking the pointer-to-pointer address, and then it's going there and grabbing the contents of that.
Good, right? It's just getting the contents at the address twice. So really, just to fully understand what's going on here, value of pointer to pointer was this. Go to the contents pointed to by this address once, so up here, and get this content, which is still a pointer, and do it again, right? I've got this pointer, and go to the contents of that address again. The address is here, and go there, right? And what's there? 7,000. Yeah.
Now, if you need pointer to pointer to pointer to pointer, or just 3 pointers, would that,
So what you're proposing, I think you're proposing 2 different things here. We could keep going, right? I can just very tediously keep drawing more stars. This will be called pointer to pointer to pointer, yeah, which grabs the address of pointer to pointer, right? That's boring, right? That's not interesting. I just keep adding more cells, and we can keep chasing the pointers, right? There's this term called pointer chasing. This means we're just chasing down where the pointer goes. And I can keep like building this example. It'd be super boring, and I could keep adding more stars. What's more interesting here? What if I do this? This is fun. What if I do this? Let me, instead of copy paste. What if we do this? Right, 3 stars. Maybe you want to take a guess what's going to happen. Yeah. Yeah, contents of 7,000. Where's 7,000? Yeah, it's up here somewhere. What's there? Who knows, right? Like the computer is not going to let us ask, right? Let's just run this program and see what happens. Who wants to take a guess at what happens? Actually, better yet, right? The compiler doesn't even like it. The compiler doesn't allow us to do it. Can we really force it to do it? Sure, maybe. Let's see how far we can push this. GCC, I'm going to turn off werr. Right? werr converts all warnings into errors that cannot compile through. Still not happy. Doesn't like compiling it at all. Maybe get rid of wall. Yeah, it really doesn't allow us to do it. Yeah, the compiler will see that we're doing something really silly and doesn't allow us to compile. Make sense? Right? How does the compiler know that we're doing something silly? Is it that smart? Like, what is it doing to figure this out?
Is it just recognizing that 7,000 isn't like a viable space of memory?
Good, right? So all of this is just type analysis. Right? It's looking at this line of code on 63, which is the silly thing that we're trying to do right now. And it's just parsing through this code and saying what we're doing something sensible, right? What it's doing is it's saying that this star dereferences whatever this is. What have I highlighted here? What's the data type of that thing that I've highlighted? Yeah. It's just unsigned int, right? Does it make sense to dereference an unsigned int? No. Right? You can only dereference pointers. Like this operator, right? The term, right? Overloading. The star means a lot of different things in different settings. Star could mean multiply, right? But star also means dereferencing. And to dereference a unsigned int makes no sense. Right? You cannot dereference an unsigned int. That's how the compiler knows that we're doing something silly. Okay, I don't think I have enough time to launch into lesson 6. So give me 2 minutes. I'll just take any more questions to clarify what's going on, right? Anybody who has had some question this whole time that could help you figure out what's going on here, yeah. Let's work through that after, yeah, because I think everybody's jonesing to get out of here. So we'll wrap it up today because I can't get through lesson 6 in the time that's left. There's going to be office hours. There's going to be recitation for 2 of the TAs this evening and afternoon. Definitely make sure to use that as a resource. Use Piazza, and good luck with the programming assignment and the quiz.
Can I just ask you a quick question about something?
Yeah.